Hello and welcome, everybody. This is a very momentous and exciting occasion where we are going to be discussing piecemeal, starting in this Facebook Live, the new textbook, Ketogenics, the science of therapeutic carbohydrate nutrition and human health. And I think from now on, we're just going to call it ketogenics because that's just a much easier word to understand. But basically, the textbook is really the handbook for clinicians, for researchers, for lay people who are interested in the topic of therapeutic carbohydrate restriction and its application for various human health conditions. And this live is all about chapter 1, which is part of the first part of the textbook, which is called Nutritional Fundamentals. So chapter 1 is obviously the fundamental part of nutritional fundamentals, namely understanding human diet and disease and looking at the scientific and evolutionary evidence specifically. So the authors include very esteemed Professor Tim Noakes, Professor Mickey Ben-Dor, and Professor Catherine Crofts. And we start by looking at the evolutionary history of human diet, and then move on into the science, and then end off with the dietary guidelines. And it's kind of a whirlwind tour that takes us through the beginnings of humanity, really, of humankind, all the way through to where we are today, and the health and brain growth trip that we've been on through these ages. So it really sets the stage, and I think it's such an exciting chapter to start with. So welcome to Professor Tim Noakes and Catherine Crofts. Welcome to both of you. Wonderful to have you. We are hoping that Mickey Ben-Dor will join us, but if he doesn't, then Prof. Noakes is more than capable of answering the questions related to the section that he co-authored with Professor Ben-Dor. But let me tell you a little bit about the authors to start with. All right, so Dr. Catherine Crofts is a New Zealand registered pharmacist and a lecturer in Australia, and her research is focused on the early diagnosis of metabolic syndrome, hyperinsulinemia, biometabolic assessment of lifestyle interventions for the management of metabolic diseases. And she has 20 years of experience as a practicing pharmacist. So welcome, Catherine. Wonderful to have you.
Thank you.
Then we have got Professor Timothy Noakes, who studied at the University of Cape Town, obtaining his MBCHB, which is medical doctor degree, as well as his DSc in medicine and exercise science. And he's now an adjunct professor at the Cape Peninsula University of Technology, following his retirement from the research unit of exercise science and sports medicine, which he co-founded. He co-founded the Sports Science Institute of South Africa back in 1995. He's also an A1 rated scientist by the NRF for his fifth year term. He's got many, many other accolades, and I could keep reading, but I'm not going to. And I think most of you really know exactly who he is. And he's also a co-founder of the Nutrition Network, the Noakes Foundation, co-authored Real Meal Revolution, and he's also co-founder of Eat Better South Africa, which is the community intervention organization that actually takes low carbohydrate nutrition into the community that needs it most, the poorer sectors of South Africa, which are actually the hardest hit by our chronic diseases and by the nutritional problems that we're facing, and it's involved in actually educating people and empowering people to take their health back. So it's wonderful to have you both. Thank you so much for joining us. So now that I have introduced the authors, okay, let me just quickly mention about Dr. Mickey Ben-Dor as well, even though he's not here, because he really adds a very important piece to this chapter. He is a paleoanthropologist, so that's very different from most of the people who we are going to be interviewing over the course of this live series, because he's not, Prof is a medical doctor and exercise scientist. Catherine Crofts is a scientist and pharmacist. I am a dietitian. So you're seeing a lot of medical focused people, as you would do in a textbook that is medically focused. But interestingly, Dr. Mickey Ben-Dor is an anthropologist. a paleoanthropologist. That means he goes back and looks at fossils, at concrete data of what humankind looked at its conception, or looked like at its conception, and he looks at evidence for what humans actually ate by looking at skeletons, by looking at isotopes. So it's a completely different area, and he adds such an important part to this chapter where he can actually show us what humans ate. And I know Prof is very familiar with his research and with the hypotheses and the theories around that, and so I'm going to be relying quite heavily on Prof Noakes to cover what Mickey Bendor would have covered, but he's very capable of that, having co-authored that section. So 3 amazing authors to start this important first chapter in this amazing textbook. So what I would like to do is, during this short live, take our listeners through the conception of humankind, of Homo sapiens, and end with where we are today, which is really what this chapter does. And we can't delve into it in the depth that we would do in the chapter. But if we can just touch on a few of the exciting aspects that are in this chapter, so that people know what they're getting in chapter 1, and they can kind of see where it's going, and they can figure out whether it's something that they really want to delve into more in more detail. So I think let's start with the first section of this chapter, which was written by Mickey Bendor and Timothy Noakes. And the first section is about the evolutionary evidence of what humans ate from the beginning. So I've kind of put together an almost theoretical or hypothetical statement, which I'd like to see if you agree with, Prof. I was going to put it to Mickey Bendor just to make sure that I'm kind of grasping it properly, because I know that I'm not as esteemed as all of you, and I feel that, you know, if I can grasp it, or put it in a way that I grasp, and hopefully our listeners also can. I know many of them are very learned as well. But my understanding is that in order to determine what a species should be eating, in other words, their species-specific diet or their evolutionarily consistent diet, we need to look at what foods they evolved eating. And this is important, my understanding is, because a species can't develop a nutritional requirement for something that was not plentiful in their environment. So you can't, like, let's say you're a giraffe, you can't develop an evolutionary requirement to eat acacias if you're not evolving alongside acacias, or lions, if you're not evolving alongside buck. You can't develop a need for eating buck without that. And as such, you know, they're probably going to be able to synthesize things that they would not be able to get from the environment, because that's just evolution, in my understanding. Or it's kind of figuring out what your body's going to learn to look for in the environment, what it's looked for during its evolution. So basically, we've evolved the need to eat basically what our bodies need. So if we look back in history, then back to what we started eating when we became human, it should give us a really good idea of what we should be eating now. And also looking back at where we were at our most healthy can also give us an indication of what we should be eating now in order to be our most healthy. So, Prof, do you think that gives us a good idea of where to start? Would you agree with the statement that we can't develop a nutritional requirement for something that wasn't plentiful in our environment?
I think that sounds perfect. Very good.
Okay, good.
So,
yes.
Carry on.
So I wanted then for us to start with the very beginnings of Homo sapiens, the very beginnings of humankind. Can you take us through your understanding of the evidence of what we would have had to, maybe start with your and Mickey Bendor's hypothesis of what diet we would have had to eat? What is the human specific, species specific diet? Maybe just encapsulate that for us, and then we'll go into the evidence for why that is. Just tell us what it is first.
Okay, so if we just go back one step, the last common ancestor that humans had with the primates were the chimpanzees. But that chimpanzee 6 million years ago, when we broke off, was not anything like the chimpanzee that we have today. They've continued to evolve. But so if you start with the basic structure of the chimpanzee was what was common to us 6 million years ago. And the key was that the chimpanzee lives on plants and fruits.
Yes.
That's what they live on. They have a small brain and a relatively, not a very well coordinated structure, social structure, because they've got to eat all the time. And if they stop eating for 20 minutes, they're in trouble. So for example, if they go on a hunt, after 20 minutes, they stop. So they do like to eat meat, but there's a restricted time zone. And once they've spent their 20 minutes, they realize it's time to get back to eating, because otherwise they're not going to get in the calories for the day. So that's the basics, that if you're going to eat plants, you need a lot of time to digest, and you need a big colon, a massive colon, and where the bacteria can digest this. And paradoxically, they produce saturated fatty acids. So although the animal is putting grass and other, not grass, but shoots and roots into the mouth, what's being digested is saturated fats. So these animals live on saturated fats. Now, somewhere along the way, prehumans realized that a better way to get your saturated fatty acids would be to kill animals that have a large amount of fat in them.
So in other words, not making. So Prof, I
Sorry?
just want to, I'm not sure it's clear. So they were getting saturated fat. Is that because they were making it in their guts? Is that because the
Correct.
bacteria?
The bacteria were making it in the gut.
But it was quite
and
an
that's why
inefficient
you have to
process.
have a lot of bacteria and a lot of space for this to happen.
Okay.
And interestingly, the protein comes from the dead bacteria as well, so that the gorillas and the chimpanzees are built on the bacteria that sit in their gut. So you have to have a big factory, and that's why gorillas look fat. They're actually not fat. They've got this huge, large colon. And that's why they can't run, they can't stand upright. To get to stand upright, you have to get rid of this large colon and make it short. And then you can get your pelvis shortens and your knees come upright directly over in line. And then you can run. And that seems to have been important for humans to start walking and running effectively. That was also part of our evolution. So Mickey's idea is that humans actually had to hunt the most difficult animals, not the weakest animals. Lions catch the weakest animals. Humans had to find the healthiest animals, because the healthiest animals had the most fat on them. And he explains that by the following, that humans evolved in a diet which had about 65% fat, and the rest was largely protein. And we have a limited capacity to use protein. I think we underestimate how much protein we can use. I think humans can eat more protein than we think, but we normally put a ceiling at about 35%. That means your other 65% of your energy has to come from something else. And the only animals that provide 65% of fat are some antelope, but elephants and rhinoceroses and hippopotamus. And so what Mickey Bendori spent his life looking at was the elephants that were being killed by early humans. And that was where he got the hypothesis that we have to eat a lot of fat. And that's how we evolved into being human. Now, that was fine until we'd wiped out all these fatty animals on all the continents, except Africa. There was still some left on Africa, but all the other continents, early humans, by now we were Homo sapiens. And as soon as we got onto these other continents, we wiped out the big animals. And then there's a problem, because now you've got to find a substitute particularly for the fat. And the substitute became carbohydrate. And that's when we had the agricultural revolution, which starts about 18,000 years ago. And then humans start become farmers, and they're living on agriculture, and their health starts to immediately decline. So there's clear evidence for that. And then in the last 100 years or so, we've developed this highly processed, ultra-processed food diet, which is completely incompatible with humans. So that in a very broad sweep, we start with eating animals, big fat animals, lots of protein, lots of fat. We kill those animals off, and then we have to start the agricultural revolution. That allows the cities to develop and humans to become socialized and develop everything we've got in our civilization, but it's the cost of our health. And then we make it even worse because we start eating ultra-processed foods. And what Catherine's going to tell us about is why humans are not any good at metabolizing carbohydrates. So because we evolved in this way to burn fat and protein, we're not really designed to eat carbohydrate. And I think the point you made when you're talking about the giraffe, you can't get the giraffe to change its dietary pattern. It will simply die. And we have examples of that in my town, in Cape Town, where they tried to bring giraffes in and they put them on the land here and it can't support them. So they died. There's another classic example that there are two types of rhinoceroses in South Africa. There's a white rhinoceros, which is a grazer, it eats grass. And there's a browser, the black rhinoceros, which eats vegetation, bushes and things. When the other rhino, the black rhino, was sent to America, they fed it grass and it died of iron overload because this animal exists in an environment which is very poor in iron. But grass, there's just a little bit more iron in grass than there is in bushes. And so this animal is able to conserve the iron, and that caused it to get iron overload. So the point is, you can't take a black rhino and make it a white rhino. It's going to die. You can't feed it the same. And that's how specialized everything is. And I think farmers know this. You can't move cattle or horses 200 miles because they start eating a different grass and the bacteria are not adapted for that grass and they get into trouble. So we are really shows us. Sorry?
No, I think that's brilliant because it really shows us that we need to be eating our own species-specific diet. Yeah. And so the question, really should be what that guides us is, what is that? And I think that's what you and Mickey Bendor have answered so beautifully in chapter 1. Now, Prof, that's really interesting about the animals. I know that you mentioned in your chapter with Mickey Bendor, you go into specific human societies. You go back into Weston Price's research. Could you tell us a little bit about what happens to traditional cultures? Now we're jumping forward from the Stone Age, where humans ate these big elephants and then killed them off and then ended up having to eat more buck or smaller things and rely more and more and more on carbohydrates as they killed off those eventually and then moved over into agriculture. And then you end up with some traditional societies who don't move over into agriculture, who maintain the hunter-gatherer lifestyle and have been studied by scientists, by anthropologists. Can you tell us what we found out by looking at those societies?
So you mentioned Weston Price. So Weston Price is a really interesting man because he's a dental surgeon, and he notices all of a sudden that the children he sees have got more cavities and their faces are becoming thinner, and they have to have more wisdom teeth removed because there's something changed in the size of the jaw, and it's become compacted and there's not enough room for the wisdom teeth. He goes to the literature and he finds some data firstly on diabetic children who in the 1920s were treated on a high-fat diet. These are insulin-dependent children who were, before the insulin came along, they were treated on a high-fat diet. And it was reported that their caries went away, their dental caries cleared up on a high-fat diet. So he thought, that's really interesting. And the second point was he went and looked at all fossils, particularly South African fossils he mentioned, and he noticed they had perfect teeth. So then he realized, okay, teeth are a barometer of how healthy your diet is. And the more caries you have, the worse the diet. So he had the hypothesis that if he were to go and look at populations around the world who continued to eat their proper diets, he would find that they had different jaw structures and they had perfect teeth. However, when the foods of the industrial era came, and those were typically sugar and other imported foods that survive, they can travel all around the world because they're highly processed, highly refined. He said, once these foods arrive, we'd expect to see a reversal of and increased ill health. So he went across 5 continents and he showed exactly that if you could find an isolated population, they would have perfect teeth, perfect jaws, and absolutely magnificent teeth. And we do show a few pictures in the book of those perfect teeth. We stole it from Weston Price's book. And so he showed the perfect structure. And then he shows you what happens in those people who had become westernized, had started eating the commercial diet. And you can see that their teeth were destroyed. And they couldn't survive. You know, it's interesting. We forget that dentists are crucial to the survival of people living this terrible food. Because if you didn't have dentists, people eating this diet would be dead because they develop abscesses in the brain from the caries in their teeth. And so the dentist saved many people, but populations living on the periphery and just becoming westernized didn't have access to dentists, so that their teeth looked terrible and they must have had awful, awful discomfort and pain. So that's the story. So he goes through those populations. And then I think one of the best stories that I discovered was Dr. Walter Yellowlees, who was a general practitioner, came back from the Second World War, 1946, went to the Scottish Highlands. And so he'd lived on the Highlands and he knew how healthy the people were. And for the next 40 years, he was their general practitioner. And he observed that the health just declined, because that's when the Scots traditionally ate animals. They had a very healthy diet. And as the animals were replaced by imported tinned goods, particularly, and sugar, their health just declined. And he said it's across the board. And there are a couple of other people, Doctors Cleve and Campbell and Yudkin. Dr. Campbell is a South African, and he was the first to notice that when African people in Natal, KwaZulu-Natal, moved to Durban and took up the Western diet, it would take 20 years and they would start to develop diabetes. So he developed this 20-year rule. And he wrote widely on it, and with Dr. Cleve wrote a famous book called The Saccharine Diseases. So he felt that sugar was the key driver. What's interesting in reflection is that wheat has been around for a long time, and refined wheat has been around, and people weren't getting the diseases they are. It was when the sugar arrives, that's when the real ill health starts. So that's just an aside.
And then, Prof,
So,
in your chapter, you also mentioned seed oils. So what role do they play? Because that's a fat.
Yeah, I think we underestimate the negative consequences, because I think we became so committed to sugar, and now we're perhaps realizing that vegetable oils are just as bad. And I think I do discuss that later on in one of the other chapters on the dietary changes introduced in 1977. And it's clear that from that moment, there was an increase. Well, actually, it occurred before that, but there was an increase in seed oil consumption, and that was also very negative on our health. But the original theory from Yudkin or from Campbell and Cleve was that it was the wheat plus the sugar that was the real problem. And also with Weston Price, they felt that the flour was also a big contributor to the problem.
Okay, so that's such a wonderful whirlwind tour, Prof, of your and Mickey Bendor's starting section within chapter 1 that takes us all the way from the start of Homo sapiens and humans and what we are supposed to be eating, what we have evolved alongside, and then when society started to get sick. And Prof Noakes and Prof Bendor, they go into all these things that Noakes has mentioned now, specifically Walter Yellowlees, the whole story is there, Yudkin, Campbell, Weston Price, it's all in there, as well as a whole lot of really interesting paleoanthropological data as well, and evidence that really makes a very, very compelling case. And I never remember the timeline, but I think the timeline is also really important, and it is also elucidated in the chapter because it shows you how really in the greater scheme of things, it's been such a tiny drop in the ocean of human history that we have been eating the way we now think is how we eat. And it kind of does explain that, maybe we haven't had very long to evolve, and maybe like those rhinos that Prof Noakes has now mentioned went to the US and suddenly was put on a different diet, maybe it is all relatively sudden for us in the greater scheme of things when looking at the overall timeline. And I think something else that I think, I'm not sure if it was you who said it or Mickey who said it, Prof, but there's a mention that everyone thinks that in the Stone Age, or okay, when humans were apparently at their healthiest, as you guys are purporting, everyone's saying, well, actually, we lived our shortest then, and surely that means we couldn't have been that healthy. But would you like to tell us a little bit of what is going on there?
Yeah, the problem is that in so-called primitive societies, there's many deaths in childbirth, and people don't live beyond, well, a lot of children die in the first 10 years of their lives. And therefore, that brings down the life expectancy dramatically. But if you could get to 20 or 30, then you could have a very long life expectancy. And we refer to the mid-Victorians who lived between 1820 and 1870. They had a life expectancy the same as today. And the reason was that
without our medical advances, that's very impressive.
Yeah. And they died of infections and trauma, which as long as you got beyond a certain age, you were less at risk of certain infectious diseases. Okay. So they lived the same life expectancy. And however, that all changes in about 1890, when the sugar comes in and the canned foods and the condensed milk starts to come in from the United States. And that's when the health of the population within one generation is impaired. For example, those in South Africa know we had the Boer War in 1900, and the British selection of soldiers had to change because in one generation, the average British person had dropped dramatically who was being recruited for the military. So they had to change the recruitment requirements. And that was all nutritional. And it was a loss of height because the food had now changed from being incredibly healthy, lots of food, lots of fresh food, fresh vegetables coming from the farms. And now that was cut when it was competing with all these imported instant foods, commercial foods.
Well, that's very interesting. So it's actually, we're looking at an average lifespan when people are saying, oh, we only lived till we were 40. That's an average because there were so many babies dying, young children dying, that it just brought down the average age. Well, actually, if you could make it beyond childhood, the life expectancy was what it is today. And I'd just like to make a note of something that Mickey Ben-Dor notes, which is that the human brain, after the introduction of these big animals, and then actually even it continued to grow when the big animals were dead and they started hunting more medium-sized animals like buck and that, because he hypothesizes because those animals were harder to catch, and we had to start using, taming wolves as dogs. We had to start using arrows. We had to start working together more. We had to use improve our physical capabilities as well as our cognitive capabilities. But he says that, we reached a brain size that was at its absolute biggest about 300,000 years ago. Humans' brain size was the biggest it ever was 300,000 years ago. And then as we moved more towards agriculture, and then humans moved into permanent settlements and became farmers, the brain size actually decreased until it got to its current volume of 13,000, 14,000 cc's. So that's really interesting to me, that actually our brain size is decreasing. And it's a little bit scary, because you'd think, wow, those, Neanderthals, obviously they're not Neanderthals, they're our own lineage. Those primitive humans, they were so stupid, but it appears that they had bigger brains than us at one stage when they were eating the evolutionarily consistent or species-specific diet. And I think that's also very telling, that our brains are shrinking. We would die without the help of dentists. We are becoming sicker, as is clearly evident from, the NHANES data and other data, which Prof goes into in his, also part of this chapter, but in his section within this chapter on dietary guidelines, which we'll talk to you a bit more about, Prof, in a minute. But I think it's actually quite scary to see the deterioration of humankind since we have not been eating our species-specific diet. So thank you for that, Prof. I think I'm going to move on to talking about your section now, Dr. Crofts. and talking about insulin resistance and hyperinsulinemia and the role of carbohydrates or any other food in that. And then before we wrap up, Prof, I think we've already touched on the dietary guidelines, but maybe we can end off. You can tell us a little bit about how the dietary guidelines, which is very recent within this whole scope of things we've been discussing, the role that they played in where we are today. And then I look forward to talking to you all tomorrow about doing a deep dive with Amber O'Hearn into the nutritional aspects of therapeutic carbohydrate restriction and the role of ketones and ketosis in that. So we'll go more into kind of the actual diet, the nitty gritty of the therapeutic carbohydrate restriction diet tomorrow in our Facebook Live. But let's talk now to Dr. Crofts a little bit about your section on insulin resistance. So your section is called Insulin Resistance, a unifying feature of chronic disease. So that's a very bold statement. You're saying that this one thing, which isn't even actually a very recognized condition. I mean, we know about type 2 diabetes, but no one really talks about insulin resistance as a condition that needs to be fought. You say, oh, yeah, obesity and type 2 diabetes and cancer, but no one's saying, oh, we need to fight insulin resistance. It's one of the biggest killers of the people in our time. No one says that. But here you're saying that this is a unifying feature. In other words, the common underlying feature of chronic diseases. And by chronic diseases, we're talking about all these things that are killing people today: heart disease, type 2 diabetes, cancer, all of these things. Can you tell us what are these? Like I've mentioned, maybe 3 of these diseases. What other diseases would this encompass? And how can you make such a bold statement?
Where would you like me to start? Okay, so one of the things is with insulin resistance is people talk about insulin resistance. Honestly, it's not my preferred term because you get both insulin resistance and hyperinsulinemia, high insulin levels, and they're 2 sides of the same coin. Because when you've got a cell, and when they talk about the literature that's happened, because one of the things that we have to remember, and it's a little bit about that history thing, is insulin was discovered as a molecule only 100 years ago. But we knew about glucose and high levels of glucose being a problem for disease 3,500 years ago. And physicians have known that when patients got high levels of glucose in their urine, all they really could do was tell those patients to put their affairs in order because they were going to die. Even with the high-fat starvation diets that Professor Notes referred to, it only bought them time. It didn't save any lives. Insulin comes along 100 years ago, and people were going, well, if we get this insulin to that people, the glucose is no longer in the urine or in the blood, and we save lives. Therefore, to control diabetes, we've got to get the glucose levels down, and we use insulin to do this. But what got overlooked is in the 1920s, Harris worked out there's 2 main types of people with diabetes. Those people who needed small amounts of insulin, and those people who seemed to be resistant to the effects of the insulin, they needed higher amounts. And he hypothesized that there's 2 types of diabetes. He referred to hypoinsulinism and hyperinsulinism, people who did not produce insulin, and hypothesized was a group of people who produced a large amount of insulin. Now, we carried on from the 20s to the 40s to the 60s, and we were able to get better measures of glucose. We were able to measure it in the blood. We developed medications to help the pancreas produce more insulin, or to help the body use insulin better. But it wasn't until the late 1960s that people first started being able to quantify insulin in tissue. And even then, it was not very precise. You know, you made up your test concentration based on units of insulin, and a unit is how much insulin it took to put a rabbit into a diabetic coma. So, you know, we've got such a poor understanding really of insulin, how to quantify insulin, that insulin resistance terms all happened about glucose. How quickly does it take to shift glucose out of the bloodstream? How much insulin does it take to move glucose out of the bloodstream? So our definitions of insulin resistance all revolved around a very glucose-centric definition. So it wasn't really until the early 70s when Joseph Kraft, a pathologist out of Chicago, started quantifying what happens when we give people an oral glucose tolerance test, what happens to their glucose levels, and what happens to their insulin levels. And he was the first really to definitively report that people with type 2 diabetes actually had high levels of insulin. But even when I was training in the late 1990s and the early 2000s, we were telling people with type 2 diabetes, which started off as adult onset diabetes, then non-insulin dependent diabetes. We were telling them, you still produce some insulin, but not enough. Or because you are overweight, your body can't use it very well. But we need to give you more insulin because your bodies aren't producing enough. Now, when we look at things almost in a physiological way, when we look at people with type 1 diabetes, they're autoimmune disease, they don't produce their own insulin. When you look at how much insulin they use over the course of the day, and this is with I'm going to say a diet that was considered to be relatively healthy for the 1960s. There's still a reasonable amount of carbohydrate, free from vegetables, some meat, but relatively unprocessed. And if we look at people on that sort of diet and how much insulin they used over the course of the day, we're talking somewhere between 20 to 50 units of insulin a day. Now, Kraft studies that looked at people with type 2 diabetes, they didn't have any insulin that day, they didn't have any medications that day, and they are producing up to, I can't think of the area under the curve calculation off the top of my head, but at varying points in time, they would have over 300 units of insulin in their blood at any one time. So they were super producers of insulin. Not all of them got up that high. But then now take those people and think about how we treat them. We're giving them more insulin. I mean, I've got patients, type 2 diabetes, who need 200 units of insulin a day. There's the ultra concentrated insulin in the United States that's needed for people who need more than 200 units of insulin as a single dose. And they might be having that twice a day. So when I started looking at insulin and trying to understand insulin resistance, and one of the first questions I was asking was actually, how much is the normal amount of insulin? But then when you look at disease states across the board, for hormonal disease states, thyroid, depression, a lot of other disease states, there's a disease state clearly associated with low levels of insulin, and a disease state clearly associated with high levels of insulin. But what is actually not really known is the impact of high insulin levels throughout the body, because we've only ever stopped to focus on insulin is needed to get glucose into blood cells. Well, it's not, because every cell within the body has got a transporter that will take glucose into the body, into that cell, without needing insulin. And then you've got cells like the neurons that have a very specific insulin receptors on them, but their glucose transporters don't rely on insulin. So the nerves rely on insulin to be healthy without, and that insulin does nothing to do with their fuel supply. So we can't say insulin is only needed to get the glucose into cells when we start looking at its impacts on the nerves. So as I said, so the nerves, neuropathies, Alzheimer's disease is starting to be referred to as type 3 diabetes. But when you look at the impact of insulin for healthy nerves, if it's too low, there's a problem. If it's too high, there's a problem. Now, a lot of this is epidemiological. When you go into the biochemistry, and I'm not going to do that today, you can see really clear pathways where the wrong amounts of insulin means the nerves can't make enough of the right proteins to stay healthy. So when the nerves start dying, all of your other body tissues are going to fail as well. But it's not just the nerves. When you start looking at the impact on the mitochondria, the powerhouse that's needed in just about every single cell within the body, I think the only ones where it doesn't really have an impact are the red blood cells. But every other cell that needs to make proteins, needs to transmit messages, needs to secrete something to keep us alive and healthy, it relies on the right amount of fuel and the right amount of fuel processing systems within the mitochondria. And when insulin levels go up, it interferes with the mitochondria. And that is where I think a lot of the insulin resistance is really coming from. It's the mitochondria not being able to process the glucose, and it starts processing glucose inefficiently to try and get rid of it. And that's fueled a lot by insulin processes. So you've got, and if the mitochondria go wrong within the body, everything else is going to fail. Slowly, but it is going to fail. And it's like what Professor Noakes was just saying with the book he was talking about. When sugar got introduced, you started seeing problems 20 years down the track. Well, other studies have shown that in people with normal glucose levels, when the insulin starts going up on a detectable basis, you can see increased rates of cardiovascular disease no more than 20 years later. So the insulin going up, and this is not without the glucose going up, this is just the insulin going up, we can see all of these problems coming through in 20 years' time. And it was what we talked to people about with type 2 diabetes, is when your type 2 diabetes start being diagnosed, we'll start seeing the major problems in 20 years' time. So we've got that 20-year window. But I think it's also really interesting that we've got that 20-year window, because if we can identify it early enough, well, maybe we can mitigate some of the effects of it. The problem that we've got is that, well, insulin resistance used to affect, and in type 2 diabetes used to affect people older than 40. Because when I first started practicing, I was told I'd never see another patient this particular patient was 28 with type 2 diabetes. And I was told, he's under 40. You'll never see another one of these when you practice. You need to study them. Well, now we've got teenagers and children being diagnosed with type 2 diabetes. So the ramifications for these people are immense. I mean, we were just looking recently at the impact that insulin has on bones. Now, it's absolutely necessary to have periods of insulin resistance. So coming back to physiology, in times when you've got lots of fruit around, temperate societies, autumn, there's a lot of food around. You eat a lot of fruit, a lot of sugar in that, your insulin levels go up, which is great because you store fat in your liver, you store fat in other parts around the bodies, but you also encourage your bones to lay down minerals really quickly. And now you've got your storage of calcium and magnesium, as probably well as other minerals being laid down, that during winter, you've still got these minerals available as well as calories from fat, so you can survive. But the problem with laying it down so quickly means you don't necessarily get good, solid growth. And you can end up with an increased amount of fragility going on. Now, when you follow up your periods of high food, high glucose, high insulin, with a period of low glucose, low insulin, i.e. winter, when everybody's got small amounts of food and you're relying on your fat stores to survive, the body moves out of anabolism and goes into catabolism. And you start repairing everything. So it didn't matter that you had a couple of months of poor bone growth, because it was followed up very rapidly by periods of low insulin, where you broke down the minerals that were laid down very quickly, and you could repair the bone structure. So what is honestly scaring me? I mean, sorry, Jan, just to slightly correct you, I'm not an Australian, I'm a New Zealander. But Auckland, New Zealand has been described as the diabetes capital of the world. And our hospitals are really proud of their renal dialysis units, where you can get the people with type 2 diabetes while they're having their dialysis the podiatrist can come through and help manage the amputations and the stump care and preventative treatment. What scares me is that in another 20 years' time, with all of these children and teenagers, peak bone growth time, who are suffering from high insulin levels, which is not very well measured, are we going to be needing very good orthopedic wards? Are we going to be seeing high rates of fragility, not just osteoporosis and porous bones, but bones that have got a high bone mineral density, but have got very poor underlying structure underneath them? That's happened because of the insulin. Are we going to be needing more and more geriatric units? Because the insulin doesn't just affect the nerves, it affects in a variety of different ways. Blood vessel health. In large vessels, you've got an increased risk of atherosclerosis. But in small vessels, nitric oxide is impaired. It's not produced, well, there's an argument as to whether it's not produced enough or whether it's produced too much, but it's being used up too quickly. Net effect is that we don't have enough nitrous oxide in the blood vessels. Nitrous oxide is a vasodilator. So our tiny capillaries get vasoconstricted. Then a little bit too much glucose. Glucose is sticky. Blood clots clump. Insulin, well, in times of low insulin, fibrinolysis occurs. Those blood clots get broken down. High insulin impairs fibrinolysis. So now we've got small, narrow blood vessels with sticky things going through them that are going to clot, which can't be cleared. That's a recipe for not just Alzheimer's disease, but vascular dementia, for renal damage, for eye damage, for blindness. It is actually really scary. So the mechanisms by which insulin is affecting all of these things is the biochemistry is complicated. And as I said, I'm not going to go into it. But we've always assumed it's due to the glucose. And I'm not denying that glucose plays a complete and utter role with all of these things. Yeah, the insulin is often doing this in the background. Oh, your glucose has gone up. It must be the glucose. But it's a combination of, in some cells, the insulin's not working. That is the insulin resistance. But in other cells, the insulin's working way too hard. And it's causing an overproduction of things, including mitogenesis. High insulin is a growth hormone. It encourages cells to divide rapidly. If cells are dividing rapidly, there's more opportunities for DNA replication to go wrong. Now, there's an argument as to whether cancer is a result of mitochondrial disorders, and the mitochondria being so impaired that it goes completely out of control, which is the Warburg effect, or whether it's the DNA and you've got extra mutations going through. It doesn't have to be one or the other with insulin. Both things are probably happening at the same time. So when you start going to the fundamentals, you start going with nerves, blood vessels, mitochondria, which leads into inflammation. It's everywhere.
Those are everywhere. Yeah. So I'm starting to really understand, and I think it's actually very exciting. I think it's very exciting. I mean, in a way, it's exciting because we've got the 20-year window to get things right, to actually help people. So that's a positive thing. But it's also exciting if it is one common underlying unifying cause of chronic disease, as you say, because that means that we can address that thing. And then all these diseases that have been growing as we have become more industrialized and adopted this non-species specific diet, just by figuring out a way to counter the insulin, we can actually solve all these chronic conditions with one bullet, if you will.
You can't actually do this with medication because you can't lower the insulin without affecting the glucose. But people who cut glucose and a large amount of refined carbohydrates out of their diets, their insulin comes down immediately, and so does their blood pressure.
It's so simple.
So do so many other issues.
So simple. So it's like, Dr. Crofts, I'm going to stop you there because we're out of time. But I just want to
And I'm just about out of battery.
Oh dear. All right. Well, this is well. We're out of time. But Dr. Crofts, I want everyone to go and read your section when this textbook comes out. It is, I'm not mincing words. It isn't easy. It isn't an easy read, because Dr. Crofts doesn't explain it, doesn't just keep surface level as she has for this talk. So there is the surface level, but if you actually go into her section, she will explain the nitty gritty. And you will learn how all of this is happening, why it's happening, which pathways it's happening with. And she includes really beautiful images to help you understand. And she's also developing a lecture to accompany this this chapter for the new Ketogenics course at Nutrition Network. So there's going to be a course that accompanies this textbook where each of the authors is going to actually go into in very like 101 level detail, because you can't obviously dive as deeply in a 1 hour lecture as you can in a chapter, but basically go over what they have explained. So please also take part in that course where Dr. Crofts explains her chapter during her lecture. But really, it's worthwhile to find out exactly what she's talking about in more detail. And I think it's fascinating. I just want to point out that my understanding of what you've said so far, Dr. Crofts, is that basically we focused on glucose, but glucose isn't, yes, it might be damaging, but it isn't the be all and end all. And neither is even insulin resistance per se, because there are times of good insulin resistance, especially when it's acute or short term or physiological in response to certain conditions, whatever, whether that's pregnancy, whatever. But it's the hyperinsulinemia chronically that is the problem. And I think you differentiate very clearly, or you make that very clear in your section within this chapter. And then going into how insulin isn't just playing a role in glucose regulation, it is playing a role in so many different tissues in different ways, but also in the same way within all of the cells of the body, such as in the mitochondria, or the microvasculature, which affects the whole body again. So again, if insulin is playing such an important role in all of the cells, throughout the body, then obviously it's going to have knock-on effects, whether that is bone conditions, whether that is dementia or Alzheimer's disease, whether that is cancer, whether that is cardiovascular disease, whether that's type 2 diabetes. I can see how it's all coming together. And I think that you make a really, really compelling argument for this. So I just want to thank you so much for that. And then, Prof, we were going to talk about the dietary guidelines, but I'm afraid we're out of time. But I think, you guys are just going to have to buy the book and read it to discover what Prof has to say about the dietary guidelines, because he's really laid the land so beautifully with Professor Mickey Ben-Dor, taking us from the conception of humanity, of humankind, what we ate and how our brains grew, how we were evolving into healthier, stronger, fitter, more intelligent humans until we weren't. And part of that is our own fault, because we had to go and kill off all the big elephants and then eventually, a whole lot of other animals. And then eventually we had to rely on agriculture, which is sad. And I think we should definitely in another book discuss the problem with humankind and doing those kind of things. But, the fact is that we've ended in this place that isn't healthy and isn't good for us. And Prof takes us on a trip now from, the 60s and then into the early 80s, when during that stage there is the development of the dietary guidelines, the American dietary guidelines, which then affected the whole world. And he explains how, and I really wanted to get into this, but just briefly, Prof really explains how it is not a scientific, it's not necessarily science, it's more politics, really. And I think that that's really key. So Prof Noakes goes into the politics of the development of the dietary guidelines, and then he looks at the data, the epidemiological data of what has happened to society since the adoption of the dietary guidelines. It wasn't just a recommendation. People actually adopted it. They listened. And since people started listening to the dietary guidelines, what has happened? They have become fatter and sicker and stupider. And I've just added the stupider because of, Mickey Ben-Dor's comments about the human brain getting smaller, but that's the truth. And it's very sad, but we have hope, because if we have a 20-year window, we can get things right. If there is one bullet, and it's not a medical bullet, it's not a bullet that any pharmaceutical company or big food company is going to profit from. This is not a profitable bullet for a capitalist society. It is a humanitarian bullet that goes back into what humans should be eating, and through all these mechanisms so beautifully explained by Dr. Crofts in her section in chapter 1, you can see how by controlling glucose and insulin, you can control all these pathological effects throughout the body to gain back your health, which is our birthright. And so I really look forward to discussing tomorrow with you a little bit in more detail with Amber O'Hearn about what this diet looks like. How do we eat this way? What are the effects going on deep within our physiology? And until then, I would like to thank our esteemed authors and speakers here today, Dr. Crofts and Prof. Noakes. Thank you so much for joining us. I really hope that everyone reads this chapter. It is fascinating, and it's something that we should all know about. Humans, we should do ourselves the service of knowing about our history, knowing about what we can do to make ourselves healthier, to make our children healthier, to make our loved ones healthier. So thank you so much for all of your hard work on doing this. And I would like to say that everyone who's given their time to author for this book, they've done it out of the goodness of their heart. This is, not a very profitable endeavor at all. This is because all of these authors want humans to be healthier and happier and take back the health that is their birthright. So really interesting, very scientific, very historical, and very interesting from a political point of view as well in this chapter. So thank you both so much. Have a wonderful evening, everybody.
Can I just thank Catherine?
Yes.
Thank you for a fabulous
for
chapter. It's really so important. When it all distilled down, it comes down to what you wrote about. And that's the difference between the way we're practicing medicine today and the way we need to practice medicine. And you've given us the biochemical basis for why we need to change. And I think that that's such a crucial component. So thank you for a fabulous chapter that you have contributed.
Thank you.
It really is. It really, really is fabulous. So thank you both so much, and thank you to our audience. And I'm so sorry we didn't have time to get to the questions. I know there were questions as well, but I hope you understand that there was just so much to get through. And maybe when you read the book, it will answer those questions. And I hope that in our live tomorrow, we can get to some more of the questions that you might have. Have a wonderful day, morning, evening, wherever you are. And thank you, authors, Prof. Noakes and Dr. Crofts. Thank you.
Thanks,
Bye.
everyone.
Okay.
Bye-bye.